Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to follow the light of the stars farther into the future than any telescope can see, toward an age when only one final star may remain in an almost completely dark universe. That last star will probably not be enormous, brilliant, or dramatic. It is more likely to be small, faint red, and remarkably patient. Long after stars like the Sun have disappeared, long after the bright spiral arms of galaxies have dimmed, it may continue turning hydrogen into helium at an almost leisurely pace. But even the most economical star cannot shine forever. Eventually its fuel will change, its structure will change, and the final steady flame of stellar fusion will go out. The universe will not end at that moment. It will simply become a place without ordinary stars, and that distinction is the quiet mystery we will explore. From your room tonight, the sky may appear almost timeless. The stars seem fixed, reliable, and far removed from the ordinary business of clocks. Yet every point of light above you is temporary. Some of those stars were born before Earth existed. Others formed much later. A few are already gone, although their light is still crossing space toward us. The night sky is therefore not a picture of one moment. It is a layered collection of different moments, delivered by light travelling across different distances. Even the sun is part of this temporary arrangement. It has been shining for billions of years, and it will continue for billions more, but its life is only one chapter in a much longer stellar story. The universe contains stars that live far more briefly, and stars that may survive for trillions of years. Cosmic longevity, rather inconveniently for anyone trying to make a simple chart, does not belong to the largest or brightest objects. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you like the video and subscribe to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. And for tonight's question, if you could safely observe one moment from the universe's distant future, would you rather see the final star still shining, or the first completely starless sky after its light has faded? Now let the room grow a little quieter. Settle into the pillow, allow your shoulders to relax, and remember that there is nothing here you need to memorize. The timescales ahead are so large that even the universe seems to lose track of the calendar, so missing a number or drifting through a sentence will not cause any difficulty. We can simply follow the story. What kind of star could survive after every familiar constellation has disappeared? Why do the smallest stars live longer than stars many times their size? Will the last star be an ancient survivor? Or could it be born much later from a rare collision? What will galaxies look like when nearly all their visible light has faded? How would anyone define the exact moment when the age of stars is over? And after the final star dies, will the cosmos truly be dark, or merely dark to eyes like ours? To begin, we need to look at the universe as it exists now. Astronomers sometimes describe the present broad period as the stelliferous era, the long age in which stars form shine and transform the matter around them. Galaxies still contain clouds of gas that can cool and collapse under gravity. Inside those clouds, denser regions contract, their centers grow hotter, and eventually nuclear fusion begins. New stars appear. At the same time, older stars reach the ends of their lives, returning some of their material to space or leaving compact remnants behind. The process is not perfectly balanced. Galaxies do not possess an unlimited supply of cold, easily used gas, and over immense periods the conditions for creating new stars will become less common. But today the universe remains brightly active. Massive stars blaze in young clusters. Sun-like stars shine steadily for billions of years. Red dwarfs glow so faintly that many nearby examples cannot be seen without telescopes. These different stars are not simply larger or smaller versions of the same machine. Their mass determines the pressure and temperature deep inside them, and those conditions determine how rapidly fusion proceeds. A massive star contains more fuel than a small star, but it burns through that fuel at a vastly greater rate. Its core is hotter, its fusion reactions are more intense, and its luminosity can be extraordinary. It lives brightly and briefly. A star like the Sun follows a slower path, but even the Sun is extravagant compared with the smallest hydrogen-burning stars. A low-mass red dwarf may contain only a modest fraction of the Sun's mass, yet it can use its fuel with exceptional efficiency and remain stable for times far exceeding the current age of the universe. The final star is therefore unlikely to win by possessing the greatest reservoir. It will survive by spending its reservoir very slowly. And to understand just how slowly, we must next enter the small, dim interior of a red dwarf where the longest stellar lives quietly begin. The stars that shine most fiercely are not the ones that remain. In the universe, brightness is often a sign of speed. A massive blue star may contain far more fuel than the Sun, but its immense gravity compresses its core so strongly that nuclear reactions proceed at a furious rate. The star becomes dazzling hot and short-lived. A small red dwarf does almost the opposite. Its gravity is weaker, its center is cooler, and its fusion reactions unfold with remarkable restraint. It may produce only a tiny fraction of the Sun's light, yet that dimness is precisely what allows it to endure. The final survivors of the stellar age will not be the stars that command attention in photographs of glowing nebulae. They will be the quiet red points that are easy to overlook, stars so faint that even nearby examples require careful observation. The universe, it seems, rewards patience more reliably than spectacle. Every stable star spends much of its life balancing two opposing tendencies. Gravity pulls the star inward, attempting to compress its matter toward the center. Energy released by nuclear fusion creates pressure that pushes outward. When those forces settle into balance, the star can remain stable for an enormous span of time. But the strength of that balance depends heavily on mass. Add more matter to a star, and gravity does not merely increase in a simple, gentle way. The added weight raises the pressure and temperature in the core, accelerating fusion. The star becomes more luminous, but the increased brightness comes at a cost. It consumes its hydrogen much more rapidly. This is rather like giving a furnace a larger supply of fuel while also opening every vent and allowing the fire to roar. The furnace may be impressive and the room may become very warm, but the fuel does not last. The comparison is imperfect, because a star regulates itself through gravity, temperature, and pressure rather than through metal valves. Still, the central lesson remains. More fuel does not guarantee more time. Massive stars demonstrate this rule in its most dramatic form. Their cores are hot enough to fuse hydrogen rapidly, and later they may proceed through additional stages involving heavier elements. Their outer layers can shine tens of thousands of times more brightly than the Sun, sometimes much more. Yet their lives may be measured in only millions of years, a brief interval by cosmic standards. They are born, blaze, and disappear while smaller stars nearby have barely changed. A sun-like star follows a calmer schedule. It shines for billions of years because its core is less extreme. But even the Sun is not especially economical. Much of its hydrogen lies outside the central region, where conditions are hot enough for fusion, and that outer material cannot simply stroll inward whenever the core requires a refill. Stars do not possess convenient fuel doors. Their internal structure determines which material can reach the active center and which material remains beyond it. Red dwarfs occupy the slow end of this stellar spectrum. They are smaller, cooler, and far less luminous than the Sun. Their surfaces glow at lower temperatures, giving them a reddish appearance, although to human eyes a nearby red dwarf might look more orange or pale than the name suggests. Inside their cores fuse hydrogen gradually. Because the star produces less energy, it radiates less energy into space, and its fuel supply declines at a far slower pace. The smallest true stars sit only just above the mass needed to sustain long-term hydrogen fusion. Below that threshold are brown dwarfs, objects too light to maintain the same stable process. Just above it, a star can shine with extraordinary frugality. It is the astronomical equivalent of a lamp turned so low that the room is barely illuminated, yet the lamp continues long after brighter lights have failed. Again, the analogy has limits. A lamp does not change its own pressure temperature or density in response to its power output. A star does all three. The difference becomes even more important when we consider how stellar material moves. In stars similar to the Sun, the central fusion region is surrounded by layers with different methods of transporting energy. Much of the hydrogen in the outer parts of the star never reaches the core during the star's main lifetime. In the lowest mass red dwarfs, however, convection can stir material through most or all of the interior. Hotter material rises, cooler material sinks, and hydrogen can be carried into regions where fusion occurs while helium is moved away. The star is not perfectly mixed at every instant, but over long periods it can access a much larger fraction of its hydrogen supply than the Sun can. This makes the red dwarf doubly patient. It burns slowly and it can use its available fuel more thoroughly. The result is a predicted lifetime not merely longer than human history or the age of Earth, but far longer than the universe has existed so far. That last point matters because no astronomer has ever observed an old red dwarf approaching its natural end. The universe is about 13.8 billion years old, while the smallest red dwarfs are expected to remain active for trillions of years. Every red dwarf we see today is therefore still young compared with the life it may eventually complete. Their distant future must be calculated through models of stellar structure, fusion convection, and energy loss. Those models are grounded in well-tested physics, but they still extend our understanding across timescales that cannot be watched directly. We can observe red dwarfs of different masses and ages. We can measure their light temperatures, magnetic activity, and motions. But we cannot point a telescope toward a naturally dying red dwarf because none should exist yet. The universe has not had enough time to make one, so the smallest stars live longest because their cores remain relatively cool, their fusion proceeds slowly, their luminosity stays low, and their internal mixing allows them to use hydrogen efficiently. They do not survive by resisting physics. They survive because physics permits them to spend their energy with almost unbelievable care. Long after massive stars have vanished, after stars like the Sun have become remnants, and after the bright patterns of familiar galaxies have faded, red dwarfs may continue glowing in the darkness. Yet their remarkable efficiency depends on something happening deep inside them, a slow circulation of matter that keeps carrying fresh hydrogen toward the center. To understand the final stars, we must now look more closely at that fully mixed furnace. A red dwarf's greatest advantage is not simply that it burns slowly, it is that much of the star can take part in the burning. Deep inside the smallest hydrogen-fusing star's matter does not remain arranged in quiet, permanent layers. Heat makes some material rise while cooler, denser material sinks, creating vast circulating currents through much of the interior. These currents are called convection. They do not resemble wind passing through open air. The star is a sphere of extremely hot, compressed plasma, and every rising or falling parcel remains buried beneath the weight of the material around it. Yet over long periods, this motion continually rearranges the star's contents. Hydrogen from farther out can be carried toward hotter central regions, while helium produced by fusion can be moved away. The result is a star whose fuel supply is not confined to one small central chamber. Its whole interior becomes part of a very slow conversation between gravity, heat, and motion. The Sun also contains convection, but it is not mixed from center to surface. In its core, energy begins with hydrogen fusion. Farther outward lies a broad region where energy travels mainly through radiation, passing from particle to particle in an indirect journey that can take an astonishingly long time. Only in the Sun's outer layers does convection become dominant, carrying heat upward through rising and sinking plasma. These regions do not freely exchange all their material. As the Sun ages, helium accumulates in its core while a large amount of hydrogen remains outside the main fusion zone. That hydrogen still belongs to the Sun, but most of it cannot simply be delivered to the center like fuel from a storage room. Stellar interiors are less cooperative than diagrams make them appear. The Sun will therefore leave much of its hydrogen unused when its stable core burning phase ends. In a sufficiently low-mass red dwarf, the internal arrangement is different. The star is cool enough and opaque enough for convection to dominate through nearly the entire interior. The exact transition depends on mass composition age and the details of the model, but stars below roughly 1/3 of the Sun's mass are commonly expected to be fully convective. In such a star, material can circulate across an enormous fraction of the stellar body. Picture a thick soup being warmed gently from below. Hotter material rises, cooler material descends, and the ingredients remain mixed rather than separating into a permanently used center and an untouched outer reservoir. The comparison helps us imagine the motion, but the star has no pot, no liquid surface, and no spoon. Its circulation arises naturally from the way energy moves through compressed plasma under gravity. Over trillions of years, that circulation allows fresh hydrogen to keep reaching regions where fusion can occur. The fusion itself proceeds through a sequence in which hydrogen nuclei are gradually combined into helium-releasing energy, because the final products contain slightly less mass than the starting material. That missing mass appears as energy following the familiar relationship between mass and energy. In a red dwarf, the central temperature is lower than in the Sun, so the reactions happen far less frequently. The star does not contain a central bonfire. It contains an immense number of rare nuclear events, each contributing a tiny amount to a steady output that can continue for ages. Gravity keeps the interior compressed. Fusion helps provide the outward pressure needed to oppose collapse. If the reactions slow slightly, the star can contract and warm, encouraging fusion to increase. If they become too vigorous, the star expands and cools, reducing the rate. This self-regulation keeps the little star stable, modest, and almost absurdly patient. Because convection repeatedly redistributes hydrogen and helium, the star's composition can remain relatively even for much of its life. It does not develop the same sharply separated helium-rich core surrounded by mostly unused hydrogen that appears in a Sun-like star. Slowly, however, the balance changes everywhere. Hydrogen becomes less abundant, helium becomes more common, and the star must adjust its temperature, density, radius, and brightness. Fully mixed does not mean perfectly unchanged. Nor does it mean that every atom follows a neat loop from surface to center and back again. Convection is turbulent, complicated, and influenced by magnetic fields rotation and other effects that remain challenging to model in detail. Still, the broad consequence is clear. A small red dwarf can use a much larger fraction of its original hydrogen than the Sun can, and it can use that hydrogen at a much slower rate. This efficiency stretches the star's lifetime into a region where direct observation becomes impossible. The universe is not yet old enough for any of the smallest red dwarfs to have completed this process. Every one of them is still somewhere near the beginning of a life that may continue for trillions of years. Astronomers must therefore combine observations of existing low-mass stars with models tested against known physics. They measure masses, temperatures, luminosities, magnetic activity, and chemical signatures, then ask whether the same equations remain reliable when carried forward through durations vastly longer than cosmic history so far. The models give a consistent general picture, but the fine details remain predictions. No telescope can show us an elderly red dwarf from the natural end of its life, because the universe has not yet produced one. Sometimes the best evidence for a future object is the fact that time has not had the opportunity to build it. For now, keep one simple image in mind: a small red star gently churning from within, carrying unused hydrogen toward the places where it can become light. This internal mixing is why the faintest stars can outlast every brilliant giant and every star resembling the Sun. It is also why the final age of starlight will unfold so slowly. But even perfect patience would not help if the universe continued making new stars forever. The last star can exist only after the great galactic nurseries have nearly closed, after cold gas has become scarce, and after the bright clouds that once formed suns have faded or dispersed. Our journey must therefore pull away from the interior of one red dwarf and return to the galaxies around it, where the supply of future stars is already beginning its long decline. Galaxies do not stop making stars because the universe suddenly runs out of matter. They stop because the right kind of matter becomes increasingly difficult to gather in the right condition. A galaxy may still contain enormous quantities of gas, but most of that gas cannot immediately become a star. It must first cool, collect into dense clouds, lose enough internal motion to collapse, and remain compressed while gravity draws smaller regions together. In the bright spiral arms of a young galaxy, this process can happen repeatedly. Dark clouds gather, dense knots form, new stars ignite, and their light begins warming the material around them. But every generation changes its nursery. Gas is consumed, stirred, enriched with heavier elements heated by radiation, or pushed away by winds and explosions. The workshop remains, but the raw material becomes harder to use. Slowly, almost imperceptibly, a galaxy begins producing fewer lights. We can already see this change across cosmic history. The universe once formed stars much more rapidly than it does today. Several billion years after the beginning of cosmic expansion, galaxies were generally richer, inaccessible gas mergers were more frequent, and many systems produced stars at rates far above those of most nearby galaxies now. Since that broad peak, the average rate of star formation across the cosmos has declined. New stars are still appearing today, including within the Milky Way, so we are nowhere near a completely quiet universe. Yet the long trend is downward. The present sky is not the opening scene of the stellar age. We've arrived after much of its most energetic activity has already passed. This does not make our era old in comparison with the red dwarfs ahead of us, but it does mean that the great machinery of star birth is no longer operating at its former pace. Some gas simply becomes locked away. When a cloud collapses to form stars, only part of its material may enter the new objects, while the rest is scattered or left behind. Later stars return some matter to their surroundings through winds or through the final stages of stellar evolution. That recycled material can join new clouds and participate in later generations. Galaxies are therefore not single-use factories. They can reuse part of their contents many times, but recycling is never perfectly efficient. Increasing amounts of matter become trapped inside long-lived low-mass stars, white dwarfs, neutron stars, planets, brown dwarfs, and other remnants. Some gas is thrown into the thin regions surrounding a galaxy. Some escapes farther. A galaxy cannot simply place an order for fresh molecular hydrogen when supplies become inconvenient. It must work with the matter that gravity motion and cosmic history have left within reach. Gas may also remain present while becoming unsuitable for collapse. Star formation prefers cold, dense regions in which gravity can overcome pressure turbulence, magnetic support, and other forms of resistance. Heat the gas, stir it too strongly, or spread it too thinly, and it may remain gaseous for a very long time without producing stars. Radiation and winds from young massive stars can break apart their own birth clouds. Supernova explosions can drive hot bubbles through a galaxy and carry material away from the disk. Near the center, an actively feeding supermassive black hole can release energy through radiation winds or jets, disturbing or heating gas across a much larger region. The black hole does not travel through the galaxy swallowing every future star. Its influence is usually less direct and more complicated. It changes the environment in which cold clouds must form. A galaxy's surroundings matter as well. In a crowded galaxy cluster, a galaxy can move through thin hot gas that fills the space between its neighbors. The pressure of that motion may strip gas from the galaxy, particularly from its outer regions. Gravitational encounters can pull material into long streams, distort disks, or redirect gas toward the center. A merger may briefly compress clouds and trigger an intense burst of star formation, only to help exhaust or disperse the available fuel afterward. Smaller satellite galaxies may lose access to the larger reservoirs that once replenished them. Their existing cold gas continues forming stars for a while, but without a fresh supply, the activity fades. Different galaxies therefore become quiet for different reasons. There is no single switch-marked star formation, which is probably just as well, because the universe has never shown much interest in convenient control panels. Even the presence of cold gas does not guarantee new stars. Observations show that some quiet galaxies retain substantial reservoirs of material that appears cool enough to be promising yet forms few stars. In these systems, rapid rotation, turbulence, magnetic fields, or the shape of the galaxy may help stabilize the gas against fragmentation. The clouds are present, but they cannot easily break into the dense collapsing pockets required for starbirth. This corrects a simple picture in which galaxies become quiet only after using or losing every trace of fuel. Sometimes the material remains, but the conditions have changed. A warehouse can be full while the assembly line has stopped. The analogy has limits because galactic gas is governed by gravity and fluid motion rather than workers and machinery. But it reminds us that having ingredients is not the same as being able to combine them. The decline will not happen everywhere at once. Large galaxies, small galaxies, isolated systems, and cluster members will follow different paths. Pockets of cold gas may survive in protected regions. Mergers may awaken temporary episodes of star formation. Material expelled long before may cool and fall back. Even after ordinary galactic nurseries have become rare, unusual interactions may occasionally assemble enough matter to ignite another star. Predicting the exact final birth is therefore much harder than recognizing the overall direction. The universe will not close every stellar nursery on the same evening. It will dim unevenly one region after another with longer pauses between each new light. As the supply of young stars decreases, galaxies will begin to reveal the lifetimes of the stars they already contain. The most massive stars will vanish first because they consume their fuel rapidly. Smaller stars will remain. the blue regions of active stellar birth will become scarce, and the average light of aging galaxies will shift toward cooler, redder populations. This sorting process will continue for periods that make the present age of the universe seem brief. New stars will no longer arrive quickly enough to replace those that disappear. One by one, the brightest members of the stellar population will leave the sky, while the quiet red dwarfs continue almost unchanged. To follow the fading accurately, we must now watch the first stars depart and discover why the most brilliant lights are also the earliest to go. The brightest stars are the first to disappear. This sounds backward at first, because a brilliant star seems powerful enough to endure almost anything. Yet its brilliance is evidence that its fuel is being spent rapidly. The hottest blue stars pour immense quantities of energy into space, illuminating the clouds around them and making young stellar nurseries visible across enormous distances. They appear dominant, but their reign is brief. While a small red dwarf may continue shining for trillions of years, the most massive stars can complete their entire lives in only a few million. In cosmic terms, they arrive and leave almost in the same moment. If we could watch a young galaxy through a greatly accelerated film, its brightest blue points would flicker out first, while the quieter stars remained almost unchanged. The universe does not preserve its most noticeable lights. It preserves the ones that ask the least from their fuel. A star cluster makes this sorting process easier to picture. Its stars usually form from the same broad cloud at nearly the same time, but they are born with different masses. At first, the cluster may contain brilliant blue stars, modest yellow stars, small orange stars, and numerous faint red dwarfs. As the cluster ages, its most massive members leave the stable hydrogen fusing stage. Their cores contract, their outer layers change, and their later evolution may carry them through swollen supergiant phases before ending in powerful explosions or direct collapse. The exact outcome depends on mass composition rotation and the influence of nearby companions. What matters for our journey is the order. The upper end of the stellar population disappears first. Remove those blue stars and the cluster becomes less luminous and less blue, even though the overwhelming majority of its smaller members remain. The connection between mass and lifetime is steep. A star several times more massive than the Sun does not merely burn several times faster. Its stronger gravity creates far more extreme conditions in the core, so the rate of energy production rises dramatically. The star has a larger supply of hydrogen, but its energy demands grow even faster than its fuel reserve. It is like a large hall heated by a furnace so powerful that the building glows through every window. The fuel store may be enormous, yet the consumption rate is even more impressive. Smaller stars resemble modest rooms warmed by low, steady heaters. The comparison cannot capture the self-regulating structure of a star, but it helps explain why the grandest stellar displays are temporary. Brightness is not a measure of how much time remains. Often it is a measure of how quickly time is being used. After the most massive blue stars have gone somewhat smaller, stars begin to dominate the visible population. White and blue-white stars continue for longer, followed by stars with masses closer to that of the Sun. This does not happen as a clean sequence across the entire universe, because new stars are still forming in some places while older populations are fading elsewhere. One galaxy may contain newborn clusters, while another has formed almost no stars for billions of years. But once star formation becomes rare, the pattern becomes clearer. Without fresh massive stars to replace those that die, blue light fades rapidly. The remaining galaxies appear increasingly red, not necessarily because every star has changed colour, but because their hottest and shortest-lived members are no longer present. The surviving light comes from cooler stars and from later stages of stellar evolution. Stars like the Sun occupy a middle position in this long departure. They are far more patient than massive blue stars, but far less enduring than the smallest red dwarfs. A Sun-like star can remain in its stable hydrogen-burning phase for billions of years. Eventually, however, hydrogen in the central region becomes depleted, the core changes, and the star expands into a red giant. Later, it releases its outer layers and leaves behind a dense white dwarf. The details vary with stellar mass and chemical composition, but stars in this general range do not end through the same violent core collapse explosions associated with much more massive stars. They fade into remnants after reshaping the material around them. By the time the final Sun-like stars complete this evolution, any planets that once circled them will have passed through history so long that their original sky's surfaces, and perhaps even their orbits, may be profoundly altered. Binary systems make the sequence less tidy. Many stars live with companions, and those companions can exchange mass merge or alter one another's development. A star that would have evolved quietly in isolation may gain fresh material and appear younger or brighter. Two smaller stars may combine into a more massive one. A white dwarf may draw gas from a companion and produce temporary bursts of light. These interactions can create luminous objects inside an otherwise old stellar population, briefly returning blue or brilliant points to a dimming galaxy. They do not reverse the overall decline, but they complicate any simple schedule. A galaxy does not age like a row of identical lamps switching off from left to right. It ages more like a large town at night, with districts darkening at different times, and an occasional window lighting again for reasons that are not obvious from far away. Over immense spans of time, however, even these exceptions become rarer. Massive stars disappear. Intermediate mass stars follow. Sun-like stars complete their transformations, and white dwarfs accumulate in the growing population of remnants. The visible universe becomes increasingly dependent on smaller and smaller stars. A galaxy that once glowed with blue clusters, pink emission nebulae, and bright yellow suns gradually settles into a deeper red. Its light grows weaker, its active nurseries become scarce, and its surviving stars are spread through a structure increasingly filled with objects that no longer sustain ordinary fusion. Gravity continues arranging orbits, carrying stars through the galaxy, and occasionally bringing systems close together. But the luminous population is being filtered by time. Eventually, the stars remaining on the stable main sequence will be almost entirely low-mass red dwarfs. These were never the most prominent members of their galaxies. They produced little visible light, hid easily among brighter neighbours, and appeared almost insignificant beside hot giants. Yet when the giants are gone, the apparent background becomes the main event. The quiet majority inherits the universe. Around them may orbit old planets, cold debris, and remnants of systems shaped across trillions of years. Between them will lie increasing stretches of darkness no longer softened by frequent stellar birth. We have now watched the brilliant stars leave the stage, and the familiar sun-like stars begin their own slow departure. Ahead lies a cosmos illuminated mainly by faint red points, the longest-lived lamps the laws of stellar physics appear able to provide. The age of red dwarfs will not begin with a single dramatic moment. No final blue star will announce that the universe has entered a new era, and no boundary will sweep across every galaxy at once. Instead, the change will become clear only after immense spans of time. New stars will appear less often. The massive stars already present will vanish. Stars resembling the Sun will age into compact remnants, and the combined light of galaxies will weaken. Eventually, almost every ordinary star still sustaining hydrogen fusion will belong to the smallest and faintest class. The universe will enter an age lit mainly by red dwarfs, modest stars that were once hidden among brighter neighbours but have outlasted them all. What once seemed like the dim background of the stellar population will become nearly the whole visible story. A galaxy in this distant period would look very different from the Milky Way we know. Today our galaxy contains glowing nebulae, bright young clusters, luminous giant stars, and a broad mixture of stellar colours. During the red dwarf age, those features would be rare or absent. The large clouds that once formed clusters would mostly have been consumed, dispersed, heated or locked into objects that could no longer return much useful material. White dwarfs, neutron stars, black holes, cold planets, brown dwarfs, and other remnants would greatly outnumber the remaining active stars. Against that dark population, the red dwarfs would appear as scattered points of weak light. A former spiral galaxy might still retain a recognizable gravitational structure, but its graceful arms would no longer be outlined by brilliant newborn stars. The architecture would remain more clearly than its illumination. Even a nearby red dwarf would provide a very different sky from the one produced by the Sun. These stars release much less energy, so a planet receiving substantial warmth would need to orbit relatively close. From such a world, the star might appear large in the sky despite being physically small, simply because the planet would be so near it. The light could seem warmer and redder than daylight on Earth, though the precise colour perceived would depend on the star, the planet's atmosphere, and the eyes doing the observing. Many planets may no longer resemble their original forms after trillions of years. Orbits can change atmospheres, can escape surfaces, can freeze or melt, and passing objects can disturb old systems. We should not casually imagine an untouched future Earth beneath a red sun. The planets of that era will carry histories almost as deep as the stars themselves. Young red dwarfs can also be magnetically restless, producing flares and streams of energetic particles that may strongly affect nearby worlds. Yet the age of red dwarfs will include stars at many different stages of their extraordinarily long lives, and their behaviour will not remain identical forever. Rotation can slow, magnetic activity can change, planetary atmospheres may be eroded, replenished, transformed, or lost depending on circumstances that vary from one system to another. It would be tempting to describe every surviving planetary system as either a frozen refuge or a quiet cradle for life, but the evidence does not allow such confidence. Habitability is not the same as habitation, and a long-lived star does not guarantee a stable home. It merely provides time, an enormous amount of it. The universe may become very generous with years while remaining rather selective about comfortable places to spend them. The darkness between these surviving systems will also deepen. Under the standard picture of an accelerating universe, sufficiently distant galaxies will continue receding until their light can no longer reach observers in a gravitationally bound local region. This does not mean that space around an observer becomes empty, or that nearby bound stars are pulled apart by ordinary cosmic expansion. Gravity can preserve local groups even while the wider universe becomes increasingly inaccessible, but the observable sky available to a far future astronomer may contain far less evidence of the larger cosmos than ours does today. Distant galaxies will redden, fade, and eventually pass beyond practical observation. The ancient radiation that helps us reconstruct the early universe will become increasingly difficult to detect. A scientist born in that era might inhabit an old island of stars surrounded by darkness and have far fewer clues that billions of galaxies had ever existed beyond it. Within the remaining bound systems, red dwarfs will continue following slow orbits through populations dominated by stellar remains. Occasional close encounters may alter those orbits. Some stars may be pushed outward and lost into intergalactic space. Others may move inward, join binary systems, exchange material, or merge. The red dwarf age will therefore not be perfectly still. Gravity never requires visible light in order to continue its work. A dim galaxy can remain dynamically active, slowly rearranging its contents across intervals beyond ordinary imagination. Most of the time, little noticeable may happen near any one star. Then, after an immense wait, a passing remnant or companion may reshape a planetary system or change the future of the star itself. The universe will seem quiet, but quiet is not the same as frozen. As the red dwarfs age, they will gradually transform the hydrogen throughout their interiors into helium. Their long stability may make them appear almost permanent, yet their composition will continue changing. Over trillions of years, the balance between pressure, temperature, density, and energy production will shift. The stars may slowly become brighter rather than simply fading from red into black. For the lowest mass examples, theoretical models predict an especially unfamiliar late phase in which a star grows hotter and less red as it approaches the end of its hydrogen supply. No such elderly object exists for us to observe today. The universe is still much too young. For now, this future star lives only in equations, a descendant of the quiet red dwarf, altered by patience into something that has never yet appeared in the sky. To continue toward the last light, we must meet this hypothetical warmer star and ask why an ancient red sun may become bluer before it finally goes dark. An ancient red dwarf may end its life by becoming less red. After trillions of years spent shining with extraordinary restraint, the star slowly changes in a direction that seems almost contradictory. Its surface grows hotter, its light becomes brighter, and shifts towards shorter wavelengths. Rather than swelling into a vast red giant like the Sun, eventually a sufficiently small red dwarf is expected to remain compact and develop into what astronomers informally call a blue dwarf. Nothing like this has ever been seen. The universe is far too young for even the oldest red dwarfs to have reached that stage naturally. A blue dwarf is therefore not an observed category of star waiting in some distant catalogue. It is a prediction produced by models that carry well-tested stellar physics far beyond the present age of the cosmos. We are looking at a future written in equations not yet in light. The change begins gradually as hydrogen is converted into helium throughout the star. Because the smallest red dwarfs remain convective for most of their long lives, helium does not simply collect inside a separate, exhausted central core, while untouched hydrogen remains far outside it. The material stays broadly mixed and the fraction of hydrogen slowly declines across much of the interior. As the chemical composition changes, so does the way the stellar gas responds to pressure and temperature. The star adjusts by contracting slightly and heating. Its fusion rate and luminosity can rise even though its remaining hydrogen supply is falling. This is not a sudden final flare. It is an extremely slow structural response unfolding over periods longer than all recorded cosmic history by an almost unreasonable margin. The star has spent most of its existence behaving like a low lamp, only to turn itself upward near the end. A sun-like star solves a similar late-life problem in a very different way. When its central hydrogen becomes scarce, fusion continues in a shell around a helium-rich core. The core contracts, the outer layers expand, and the star becomes a red giant. Its surface cools even as its total luminosity rises because the energy escapes through an enormously enlarged area. A very low-mass red dwarf does not develop the same sharply separated internal structure, and its late evolution does not require the same vast expansion. It can remain physically small while increasing its surface temperature. One star grows brighter by becoming enormous. The other grows brighter by becoming hotter. It is a little like needing to illuminate a room more strongly and choosing between building a much larger lampshade or increasing the temperature of a compact source. Stars naturally manage this without consulting an interior decorator. The name blue dwarf should be handled carefully. It does not mean that the star would necessarily appear as a vivid blue jewel to human eyes. Astronomical color names describe temperature and spectra more than ordinary visual impressions. The future star would be bluer than the cool red dwarf it once was, perhaps appearing pale or whitish, depending on its exact temperature and on the observer. The important change is physical. More of its energy would emerge at shorter wavelengths, and its surface would become much hotter than during most of its main sequence life. It would still be small compared with a giant star. Its late brightness would not come from a greatly expanded radius, but from a hotter compact surface radiating more energy. The word blue is useful, it is not a paint sample. For any surviving planets, this transformation would alter the system slowly but profoundly. A world that had spent trillions of years in deep cold might receive increasing warmth as its star brightened. The region where liquid water could exist under suitable atmospheric conditions would move outward. Yet such possibilities should not be mistaken for predictions of life. By then, planetary atmospheres may have escaped, surfaces may have been reshaped, orbits may have shifted, and close encounters with other objects may have disturbed the system. Some worlds may no longer exist in recognizable form. Others might remain frozen airless or chemically transformed. The star's brightening provides energy, not a guarantee of habitability. Still, the image is quietly remarkable. After ages of fading galactic light, an ancient little star may warm some of its distant worlds more strongly near the end than it did through most of its life. Eventually, even this hotter phase must finish. The remaining hydrogen becomes too scarce for sustained fusion to support the star in its familiar form. The star does not contain enough mass to proceed through the sequence of heavier element fusion available to massive stars. Nor is it expected to end in the core collapse explosion that destroys a giant star. Instead, the exhausted object contracts toward a compact remnant supported by the quantum behavior of densely packed electrons. It becomes a low-mass white dwarf, at first retaining heat left from its long evolution, and then cooling gradually into the darkness. The transformation from red dwarf to blue dwarf, and then to white dwarf, is smooth in models, although the exact path depends on mass composition, opacity, convection, and details that cannot be tested by watching a complete example today. That limitation matters. The general physics behind these predictions is strong, but the future being described lies trillions of years beyond direct observation. Small differences in a star's initial mass or chemical composition may alter its lifetime and late appearance. Magnetic fields, rotation, mass loss, and binary companions could complicate an otherwise simple path. The term blue dwarf itself refers to a theoretical stage, not a population astronomers have detected. Science can describe the likely direction of the journey more confidently than every detail along the way. The faint red star should grow hotter, exhaust its hydrogen, and settle into a remnant. But before we enter that remnant-filled universe, we must widen our view once again. By the time the ancient red dwarfs begin turning bluer, the cosmos around them will already be crowded with the quiet remains of stars that finished their lives long before. When the final ancient red dwarfs approach the ends of their lives, the universe will already contain far more stellar remains than shining stars. Most of the bright objects that once outlined galaxies will have been transformed into compact remnants, cold, substellar bodies, planets, and scattered debris. The galaxies themselves may still be held together by gravity, but their visible appearance will have changed almost beyond recognition. Spiral arms will no longer glow with young clusters. Nebulae will no longer be illuminated by nearby blue stars. Instead, an observer with sufficiently sensitive instruments would find a dim population of white dwarfs, neutron stars, black holes, brown dwarfs, and surviving low-mass stars moving through an enormous darkness. The age of starlight will be giving way to an age of remnants. It will not be empty. It will simply be difficult to see. White dwarfs are expected to form much of this hidden population. They are the exposed cores left behind when low and intermediate mass stars complete their ordinary fusion lives and release their outer layers. A white dwarf may contain a mass comparable to the Sun compressed into an object roughly the size of Earth. It no longer supports itself through sustained fusion in its center. Instead, its collapse is resisted by the quantum behavior of electrons, which cannot all be forced into identical states. This produces what physicists call electron degeneracy pressure. The phrase sounds rather formal for something so useful. In simple terms, matter at that density develops a resistance to further compression that does not depend on the star remaining hot. Gravity presses inward, and the structure of quantum matter pushes back. A newly formed white dwarf can still glow intensely, because it begins its remnant life extremely hot. That light is stored thermal energy escaping into space, not the steady replacement of energy through ordinary core fusion. With no long-term furnace replenishing what it loses, the white dwarf cools. Its light weakens, its surface temperature falls, and its interior eventually begins to crystallize. Given a sufficiently long time, it should approach the hypothetical state known as a black dwarf, a white dwarf, that has radiated away so much heat that it emits almost no detectable light. No black dwarfs exist today. Even the oldest white dwarfs have not had nearly enough time to cool that far. Like blue dwarfs, black dwarfs belong to the expected future, rather than the observed present, and their exact evolution depends on assumptions about matter over almost unimaginable durations. Neutron stars form a smaller but still remarkable group of remnants. They are created when the cores of certain massive stars collapse, compressing more mass than the Sun into a sphere only about the width of a city. Matter inside them reaches densities that cannot be reproduced in ordinary laboratories, and the precise behavior of their deepest interiors remains an active scientific question. Some begin their remnant lives spinning rapidly and producing beams of radiation, appearing to distant observers as pulsars. But rotation slows, magnetic activity evolves, and the beams may eventually weaken or cease to cross any observer's line of sight. The neutron star remains even when its pulse can no longer be detected. It continues travelling through its galaxy as an extraordinarily dense, increasingly cold object, carrying the compressed remains of a star that once shone millions of times more brightly. The most massive stellar remnants are black holes. A black hole does not possess a material surface from which ordinary light can escape. Its presence can be revealed when nearby matter falls inward, heats up and radiates before crossing the event horizon, or when the black hole's gravity affects other objects. In the remnant universe, however, usable surrounding material will often be scarce. Many black holes may spend extraordinary intervals almost entirely dark, moving through old stellar systems without a bright accretion disk to announce them. Supermassive black holes may remain near the centers of gravitationally bound galactic remnants, while smaller black holes continue on orbits shaped by encounters, mergers, and the slow rearrangement of their surroundings. They will be among the longest-lasting large structures in the universe, although their ultimate future belongs to a much later chapter than the death of the last star. Not everything in this era will be the remains of a former star. Brown dwarfs were never massive enough to sustain the ordinary hydrogen fusion that defines main sequence stars. They begin warm from their formation and contraction, then gradually cool and fade. Planets, moons, asteroids, comets, and fragments of former planetary systems may also persist, although their original arrangements cannot be assumed to survive unchanged. Passing remnants may disturb their orbits. Central stars may lose mass. Systems may exchange objects or eject them into interstellar space. A planet could spend ages circling a cooling white dwarf, drift around a brown dwarf, orbit a neutron star, or travel alone after being released from its system. Darkness will contain an enormous inventory of worlds, but few convenient lamps by which to notice them. This remnant universe will not be perfectly still. Gravity continues whether an object shines or not. White dwarfs may orbit other white dwarfs. Neutron stars may travel with companions. Black holes may form binaries and gradually draw together as they lose orbital energy through gravitational waves. A passing star or remnant may scatter planets, exchange companions, or throw another object out of a bound system. Occasionally, two compact bodies may merge, releasing a brief outpouring of energy into a cosmos otherwise starved of light. Old planetary debris may fall onto a white dwarf and glow for a time. Gas may collect around a black hole and become hot enough to radiate. Such events will become rarer as systems spread, merge, or lose members, but the end of ordinary fusion does not place gravity into retirement. It has never required an audience. How long these remnants endure depends partly on questions that physics has not yet settled. We do not know whether protons eventually decay, whether dark matter particles transform or disappear, or whether unknown processes become important over durations far beyond anything accessible to experiment. Even the stability of matter cannot simply be assumed forever without qualification. Models can describe likely pathways, but confidence decreases as the timeline extends. The remnant era is therefore not a fixed photograph of the future. It is a carefully constructed scientific forecast, strongest in its broad direction and less certain in its most distant details. Still, one conclusion remains clear. After most stars are gone, the universe will retain structure, motion, heat radiation, and opportunities for rare encounters. The former galaxies will become dark collections of remnants, rather than completely empty spaces, and among the brown dwarfs and other low-mass bodies moving through those collections, gravity may occasionally bring two objects together with enough combined mass to begin hydrogen fusion once again. Long after ordinary stellar nurseries have faded, a new star may unexpectedly appear. To discover whether such late arrivals could become the true final stars, we must next watch the dark objects collide. A dark galaxy may still have one more way to make a star. Long after its great molecular clouds have vanished, and long after ordinary stellar nurseries have stopped producing clusters, it may retain enormous numbers of brown dwarfs. These objects are often described as failed stars, although the phrase is a little unfair. A brown dwarf forms much as a star does through the contraction of gas under gravity, but it never gathers enough mass to sustain the stable hydrogen fusion that powers an ordinary main sequence star. It begins warm shines, faintly with energy left from its formation, and then cools. By the remnant era, most brown dwarfs would be almost completely dark. yet the hydrogen inside them would remain largely unused. They would be cold containers of stellar fuel drifting through old gravitational systems and waiting without intention or impatience for an exceptionally unlikely encounter. If two brown dwarfs collide or merge, their combined mass may rise above the threshold required for sustained hydrogen fusion. The result would not ignite like a match the instant the objects touch. Their meeting would be turbulent. Gas would be compressed and heated, some material might be thrown away, and the merged body could rotate rapidly. If enough mass remained bound, gravity would slowly pull the object into a more compact shape. As it contracted, its center would grow hotter until hydrogen fusion could begin. A new low-mass star would then appear in a universe where conventional star formation had nearly ended. It would not be born inside a glowing nebula surrounded by hundreds of siblings. It might emerge alone among white dwarfs, cold planets, black holes and other brown dwarfs, a small point of steady light in a region that had been dark for an immense span of time. This possibility does not mean that brown dwarfs frequently crash together. Space remains spacious even inside a galaxy, and the direct collision of two objects is rare. Their chance of meeting depends on how many brown dwarfs exist, how densely they are gathered, how fast they move, and how long their gravitational system remains intact. Close encounters may sometimes allow two objects to become a bound pair. Existing brown dwarf binaries may also lose orbital energy very gradually and merge. But as an old galaxy evolves, gravitational interactions can eject many of its members into intergalactic space, where encounters become even less likely. The late production of stars would therefore decline with time. The process is best imagined not as a new generation filling the galaxy, but as an occasional lamp appearing after the building's been dark for ages. The collision must also satisfy more than a simple rule of addition. Two brown dwarfs might possess enough combined mass on paper, yet fail to leave behind a stable hydrogen-burning star. A violent encounter can eject part of their material. Too much angular momentum could prevent the merged object from settling easily. A grazing collision might pull the bodies apart or leave a complicated bound system, rather than one quiet star. The final outcome depends on the mass's approach speed, impact angle composition and surrounding environment. Numerical models have shown that suitable encounters can produce a body above the hydrogen-burning limit, but carrying that result into the remote future requires assumptions about the population and motion of objects that no telescope can test directly. The mechanism is physically plausible. Its exact future importance is uncertain. When such an object succeeds, the star it creates should usually be small. Brown dwarfs begin below the stellar mass threshold, so combining two of them naturally produces something near the low mass end of the main sequence, unless the participants are unusually massive or additional material is involved. This gives the newborn star another long life. After contracting and settling into balance, it may burn hydrogen slowly, much like the red dwarfs that dominated the earlier stellar age. Its light could continue for trillions of years, extending the era of fusion far beyond the natural lifetimes of stars born in ordinary gas clouds. In that sense, the late universe may recycle not gas, but entire substellar bodies. Two objects that never became stars separately could succeed together. The universe does not offer many second attempts, but gravity occasionally arranges one. Other mergers may add further complications. Two low-mass stars could combine and produce a more massive star with a shorter remaining life. Mass exchange in an ancient binary might expose fresh fuel or alter the evolution of one member. Compact remnants could collide and create brief bursts of radiation without forming a long-lived hydrogen-burning star. These events would make the fading of the stelliferous era uneven. There might be vast intervals containing no newly formed stars, followed by the appearance of one faint red point. That star would shine age and become another remnant. Much later, somewhere else inside a surviving bound system, another merger might repeat the process. The final pages of stellar history may contain wide blank spaces between a few scattered lines. From a distance, one of these late-born stars would seem almost impossibly isolated. There may be no bright galactic disk behind it, no blue companions and no luminous cloud marking its birthplace. The wider universe could already have faded beyond observation from its local region. Around the star might circle debris captured during the merger, or perhaps no organized planetary system at all. Any planets that did form or survive would inherit a strange sky, dominated by one modest sun and a sparse population of dim remnants. Yet the star itself would obey familiar physics. Gravity would press inward. Fusion would provide pressure and light. Hydrogen would gradually become helium. Even at this remote stage, the old stellar balance would briefly return. These rare births make our original question more difficult. The last star may not be one of the primordial red dwarfs that simply survives longer than its neighbours. It may be a star assembled much later from brown dwarfs or other low-mass objects. The oldest star and the final star need not be the same object. One is determined mainly by endurance. The other may be determined by chance. To identify the true final light, we must decide what we mean by a star being last. The last one born in a gas cloud, the last ancient survivor, or the final successful merger to ignite after an age of darkness. The last star is not necessarily the oldest star. That distinction becomes important once ordinary star formation has nearly ended, and rare mergers begin adding unexpected lights to the dark. An ancient red dwarf may survive for trillions of years because it burns its hydrogen with extraordinary patience. Yet somewhere else much later, two brown dwarfs may collide and assemble a new low-mass star whose life begins after the ancient dwarf has already spent most of its fuel. The older object may have endured longer in total while the younger one shines later on the cosmic clock. So when we ask which star will be the last, we are really asking several questions at once. Which star is born last? Which existing star lives longest? And which object performs the final sustained act of hydrogen fusion? The last star, formed by familiar means, would be the final product of a cold gas cloud collapsing under gravity. It might appear in a small protected reservoir long after most galaxies have lost the ability to make stars regularly. No one can identify where that cloud will be, what galaxy will contain it, or when it will collapse. Star formation declines unevenly, and the materials required for it can survive in scattered pockets. A cloud may remain too warm or diffuse for ages, then become compressed by an encounter or merger. Another may be stripped away before it can form anything. The final conventional stellar birth will therefore be decided by local circumstances that cannot be projected across trillions of years with precision. The universe has not prepared a guest list, and the last arrival is unlikely to announce itself. The longest-lived stars born during the ordinary stellar age should be found near the low-mass edge of hydrogen fusion. They begin with little mass produce, little light, and can mix much of their hydrogen through their interiors. A sufficiently isolated example could remain active long after brighter populations have become white dwarfs, neutron stars, or black holes. But isolation cannot be guaranteed forever. A red dwarf may have a companion. It may exchange matter merge, or be scattered by a close encounter. It may be ejected from a weakening gravitational system and travel alone through intergalactic darkness. Some of these changes could shorten its life. Others could supply fresh material or produce a new object. The star with the ideal mass for longevity is not automatically the star that receives the quietest history. Then there are the late-born stars assembled from brown dwarfs or other low-mass bodies. Their formation depends on encounters that should become increasingly uncommon as old systems lose members and expand. Even so, an extremely rare event can matter when the available time is enormous. One successful merger may create a small red star after a dark interval, far longer than the entire present age of the universe. That star could then shine for trillions of additional years. Much later, another merger might occur elsewhere. The final era of starlight may therefore resemble a shoreline seen through fog, long stretches with nothing visible, followed by one distant point, then darkness again. There may be no clean moment when everyone could agree that stellar birth has ended, because the next improbable ignition could always lie beyond another immense wait. To call one object the true final star, we must use a practical definition. It would be the last object anywhere within the relevant future cosmos to sustain ordinary stellar fusion, regardless of whether it formed from a gas cloud, survived from an earlier age, or emerged through a merger. This definition sounds simple until the word anywhere is examined. Accelerated expansion divides the far future into regions that cannot exchange signals. A final star in one gravitationally isolated region could never be compared with a final star beyond its cosmic horizon. No observer would be able to survey the entire universe and confirm that no more distant star remained. The phrase, "the last star in the universe," is therefore a global idea supplied by a model, not an event any single astronomer could verify from one location. Even within one bound region, predicting the winner would be almost impossible. Tiny differences in initial mass affect a red dwarf's lifetime. Chemical composition changes its structure and fusion rate. Binary companions alter the available fuel. Encounters can remove, add, or rearrange matter. Brown dwarf mergers depend on population density, orbital motion, and chance. The literal final star may be determined by an event so rare and local that no broad average can specify it. Science can identify the kinds of objects most likely to compete. It can describe the mechanisms that make them last. It can estimate the eras in which they should dominate. But it cannot assign a name, location, and final appointment. A trillion-year calendar would already be an awkward object. The last star would still refuse to make a booking. What we can say is that the final star should be modest rather than magnificent. Whether ancient or newly assembled, it will probably have a low mass and a slow fusion rate, because those qualities extend its life. It may shine alone among cold remnants with no bright spiral galaxy visible around it, and no distant galaxies accessible beyond its local horizon. Its light will not mark the end of all activity, only the last sustained conversion of hydrogen into stellar radiance. Eventually, however, even this survivor will change. Its remaining fuel will diminish, its internal balance will shift, and fusion will no longer support the familiar form of a living star. We cannot point to the object, but we can follow the physics of its final transformation. The search for the last star now becomes the story of its last flame. The final star will not go out like a lamp switched off in an empty room. Its ending will be slower, quieter, and far less sharply defined. For an immense span of time, it will continue balancing gravity against the pressure created by energy moving outward from its interior. Hydrogen nuclei will still combine, helium will still accumulate, and a faint stream of light will cross the surrounding darkness. But the available hydrogen will gradually decline. The star's internal composition will change, its structure will adjust, and the rate of fusion will become increasingly difficult to sustain. There will be no audience gathered around it, and perhaps no living observer anywhere nearby. Yet the same physical conversation that shaped every ordinary star will continue to its final sentences, gravity pressing inward, heat, resisting collapse, and a diminishing supply of fuel deciding how long the balance can last. If the final star is a very low-mass red dwarf, much of its hydrogen will have been used far more efficiently than the Sun can use its own. Convection will have carried material through most of the interior, allowing fusion to draw from a broad reservoir rather than from one isolated core. Over trillions of years, however, even this advantage will run out. The proportion of helium will rise throughout the star while hydrogen becomes increasingly scarce. The star may contract slightly and grow hotter, passing through the predicted late phase, in which it becomes less red and more luminous. But brighter does not mean renewed. It is the result of the star changing its structure as the remaining fuel becomes harder to use. The final light may therefore strengthen for a time before beginning its last decline, like an ember, briefly glowing more clearly when its surroundings shift, though the stellar mechanism is far slower and governed by gravity rather than moving air. The exact path would depend on what kind of object becomes the literal last star. An ancient red dwarf born during the ordinary age of star formation would likely have a relatively simple chemical history, although encounters and companions could still alter it. A star created much later through the merger of brown dwarfs might rotate rapidly, contain unevenly mixed material, or lose some mass during its formation. A binary companion could transfer matter and delay or complicate the ending. These possibilities prevent us from describing one guaranteed final sequence. Still, a low-mass star does not have enough central pressure and temperature to continue fusing progressively heavier elements in the manner of a massive star. It will not build an iron core and end in a great core collapse explosion. Its departure from the main sequence should be much gentler. The last star is expected to leave no brilliant supernova behind, only a gradual change from active fusion to compact remnant. As hydrogen fusion weakens, gravity does not simply crush the star without resistance. The interior becomes increasingly dense, and the quantum behavior of electrons begins supporting the contracting object. Electrons cannot all occupy the same available states, so compressed matter develops a pressure that does not depend on continued nuclear burning. This electron degeneracy pressure can hold the remnant against further collapse. The former star settles toward the state of a low-mass white dwarf, compact, dense, and still hot from the energy stored within it. The process is not quite a star dying and leaving another object behind as though one body were exchanged for a different one. It is the same matter moving into a new physical arrangement. The active stellar furnace ends, the remnant remains. Even the phrase "the moment fusion stops" requires care. Inside an aging star, nuclear reactions do not necessarily cease everywhere at one perfectly synchronized instant. They become less effective as fuel and structure change. Weak or localized reactions may continue after the star can no longer maintain the stable balance that defined its long, main sequence life. Astronomers often classify stages using the dominant source of energy and the object's overall structure, but nature does not always provide a crisp border. There may be a final individual fusion reaction somewhere in the cooling interior, but that microscopic event would not be the most meaningful ending. The important transition is the loss of sustained fusion as the process supporting a star-like state. After that, no remaining object anywhere in the relevant universe would continuously turn hydrogen into the steady light of an ordinary star. The newly formed remnant would still shine. Its surface could remain hot, and stored thermal energy would continue escaping into space. For a distant observer, the final star's disappearance would therefore not produce instant total darkness. The steady light generated by fusion would be over, but the white dwarf left behind would glow as it cooled. Other remnants might also emit weak radiation. Matter falling toward a black hole could briefly become luminous. compact objects might collide. Ancient particles and background radiation would still cross space. The end of the final star is therefore the end of one particular source of light, not the disappearance of every photon. The universe would lose its last sustained stellar flame while retaining a faint and scattered afterglow. There is something almost modest about this ending. The first stars transformed a dark young universe by producing light heavier elements and the ingredients from which later planets could form. The last star will perform the same basic act on a far smaller stage, combining hydrogen into helium, while everything around it has grown old and dim. Its final fusion will not shake the whole cosmos. Distant regions, if any remain causally accessible, will not respond. Gravity will continue guiding dark objects along their paths. Space will continue expanding. The last star will simply cross a threshold that countless stars crossed before it, except that this time no ordinary stellar light will remain elsewhere to take its place. And so the final flame ends not with a sudden blast but with a balance quietly lost. The star contracts, fusion fades, quantum pressure supports what remains, and a white dwarf begins its long, cooling journey. Somewhere in the darkness, the last continuous source of ordinary starlight becomes a remnant. Yet the sky does not become perfectly black at once. Heat still escapes, radiation still travels, rare events may still flash across the silence. To understand the first universe without stars, we must now look beyond the final fusion reaction and ask what kind of night begins after the last stellar light has started to fade. The first night without stars would not arrive everywhere at once. There would be no universal sunset, no final beam crossing every region of space at the same moment. By then, cosmic expansion would have separated distant gravitational communities beyond one another's horizons, and each surviving region would experience its own slow transition. The phrase "the first starless night" is therefore a useful image rather than a precise date on a cosmic calendar. Within one old, bound collection of remnants, the final hydrogen-fusing star would complete its transformation, leaving no ordinary star nearby to replace it. A sky that had already contained only one faint point of steady light would lose that point. Yet the darkness would not be absolute. The last star's remnant would still be hot, radiation would still travel through space, and gravity would continue moving unseen objects along their ancient paths. The white dwarf left by the final low-mass star could remain visible for a very long time. Although sustained fusion had ended, the compact object would contain stored thermal energy, slowly escaping from its surface. At first it might shine more brightly than many of the old remnants around it. Then it would cool, shifting toward lower temperatures and weaker light. The process would be almost unimaginably gradual. There would be no evening when a distant observer watched the white dwarf visibly dim from one moment to the next. Its fading would be revealed only by comparing measurements separated by enormous intervals. A white dwarf is rather like a stone removed from a fire, except that this stone may contain a substantial fraction of a star's mass, compressed into a body roughly the size of a planet. The analogy captures the cooling, but not the extraordinary density, quantum pressure, or duration. Other white dwarfs would also continue releasing their stored heat. Some could retain thin outer layers capable of limited residual nuclear reactions, while others might be warmed temporarily by falling debris or interactions with companions. Neutron stars could emit weak thermal radiation, or release energy through their magnetic fields and rotation, although these sources would generally fade as the remnants aged. Black holes would remain dark when isolated, but matter approaching one could become hot and luminous before crossing the event horizon. A cold planet asteroid or cloud of gas disturbed from an old orbit might briefly create a faint accretion glow. These events would not restore the age of stars. They would be after images and interruptions, energy released by remnants and motion, rather than by stable hydrogen fusion. The background of the universe would also contain radiation left from earlier ages. Photons produced by stars would continue traveling unless absorbed or scattered. The cosmic microwave background, already cold and stretched by expansion, today would become colder still and shift toward wavelengths increasingly difficult to detect. From the perspective of hypothetical eyes like ours, the universe would be almost entirely black. But darkness is partly a statement about the observer. Instruments sensitive to radio waves, infrared radiation, energetic particles, or gravitational waves could still reveal activity invisible to ordinary sight. A dark room may contain warmth, sound, and moving air even when the lamps are off. In the same way, a starless universe could contain many physical processes while offering almost no visible scenery. Any observer living in this era would face an unusual problem. Much of cosmic history might be extremely difficult to reconstruct. Distant galaxies could have passed beyond the observable horizon of the local bound region. The ancient background radiation might be stretched to such long wavelengths that detecting it would require technologies and scales difficult to imagine. The old remnants nearby would reveal that stars had once existed, but the larger structure and early history of the universe might be hidden. A far future astronomer could examine white dwarfs, planets' heavy elements, and scattered debris and infer that brighter times had come before. Still, the star-filled cosmos visible to us would no longer be available for direct study. We live while the evidence is unusually generous. The universe currently allows us to see both young stellar nurseries and light that has crossed space for billions of years. Even the word night would have changed meaning. Night on Earth is produced when the planet turns away from the sun while stars remain visible beyond the atmosphere. In the remnant era, there may be no warm world with a rotating surface, no atmosphere, and no nearby observer dividing time into day and night. The darkness would surround nearly every object continuously. A planet orbiting a cooling white dwarf might still experience a faint day and a darker night, but as the remnant cooled, the distinction would weaken. A wandering planet with no luminous companion would carry its darkness with it. The first night without stars would not be a view from a familiar field beneath a black sky. It would be an entire environment in which ordinary daylight had become a memory preserved only in matter. Yet the darkness would not be motionless. Compact objects would continue orbiting one another. Gravitational encounters would slowly alter old systems. Debris could fall onto remnants. White dwarf pairs might draw closer neutron stars, or black holes might merge, and occasional collisions could release brief flashes or gravitational waves. Most regions would remain quiet for durations that overwhelm any human comparison, but the laws of physics would not pause between visible events. The universe would resemble a vast clockwork mechanism operating in a room whose illuminated face had disappeared. Its movements would be difficult to notice, but they would continue all the same. So the first starless night would be neither perfectly black nor completely inactive. It would mark the end of sustained ordinary starlight, not the end of radiation, heat, gravity, or change. Cooling remnants would provide a diminishing afterglow. Rare encounters would interrupt the darkness. Background photons would stretch across expanding space, becoming colder and harder to detect. And beneath the absence of visible stars, gravity would keep rearranging the remains of the luminous universe. To follow the story farther, we must leave the vanished sky behind and listen instead for what still happens in the darkness. Darkness does not bring the machinery of the universe to a stop. After the final ordinary star has ceased sustaining fusion, the old gravitational systems around it will continue to move, although their motions may be almost impossible to notice on any familiar timescale. White dwarfs, neutron stars, black holes, brown dwarfs, planets, and smaller debris will follow orbits inherited from vanished galaxies. Some objects will remain paired, others will travel alone through the fading outskirts of bound systems. Most will pass one another at enormous distances, exchanging only tiny gravitational nudges. Yet tiny changes accumulate when time is abundant. An orbit can slowly widen, tilt, or become more elongated. A close encounter can transfer energy from one object to another, sending one inward and another outward. The starless universe will not be a still photograph. It will be a long, dim rearrangement. In an old gravitational system, repeated encounters can gradually sort objects by mass and motion. A relatively light planet or brown dwarf may gain enough orbital energy to escape, while a heavier remnant settles toward the denser central region. This process is not organized and does not lead every object along the same path. It is statistical, built from countless encounters whose individual effects are small and whose final results depend on chance. Over immense intervals, a former galaxy can lose members one by one, rather like a loosely gathered group of travelers slowly taking different roads. The comparison is useful only up to a point. The travelers are not choosing, the road's not fixed, and a gravitational encounter can redirect an object without the two bodies ever touching. Eventually, much of the surviving population may be scattered into deep space, while a smaller collection of massive remnants remains bound more tightly near the center. Binary systems provide another source of motion and occasional light. Two white dwarfs, two neutron stars, or two black holes may orbit a shared center of mass. According to general relativity, an accelerating pair can carry energy away in the form of gravitational waves, causing the orbit to shrink. For widely separated objects, this change may be extraordinarily slow. For closer pairs, it can eventually end in a merger. The final approach may release a strong signal in gravitational waves, and some combinations can also produce electromagnetic radiation or eject material. These events would be rare in the late remnant era, but rare is not the same as impossible when the universe has almost unlimited patience. Between them may lie intervals so long that the entire age of stars would seem brief. Then two dark objects meet, space-time carries the news outward, and the universe becomes momentarily less quiet. White dwarfs can also gather material from their surroundings. A disrupted asteroid, a surviving planet, or matter transferred from a companion may fall toward the compact remnant. As it descends through the white dwarf's gravity, the material can heat and radiate, producing a temporary glow. Under some conditions, accumulated material may trigger nuclear reactions near the surface or contribute to a much larger explosion, although the available systems and fuel will become increasingly scarce. Black holes can brighten in a similar indirect way. The black hole itself does not shine through an ordinary surface, but gas or debris spiraling inward can become extremely hot before crossing the event horizon. In a universe with little loose material, most black holes may remain nearly invisible for extraordinary periods. A brief accretion event would be less like a restored sunrise than a small spark caused by the movement of ancient remains. Not every event in the darkness will create visible light. A planet may be ejected without glowing. Two black holes may merge in a region containing almost no gas, sending gravitational waves through space, while producing little or no electromagnetic signal. Cold objects may exchange companions, break apart old planetary systems, or fall into larger remnants. Even galaxies, or what remains of them, may continue merging within a gravitationally bound region. Their stars would no longer outline the encounter, so the collision could be almost entirely hidden. Dark matter, if it remains stable and behaves as current models suggest, would continue contributing most of the gravitating mass in these systems even though its fundamental nature is still unknown. The future depends partly on questions like this. It also depends on whether protons are perfectly stable, whether unknown particle processes alter matter, and whether our description of dark energy remains valid across durations beyond any experiment. Black holes carry the story still farther. Quantum theory applied to curved spacetime predicts that an isolated black hole should emit Hawking radiation and lose mass, but this radiation has not been detected directly from astrophysical black holes. Under the standard prediction, black holes would persist long after stars and many other recognizable structures had disappeared, with the most massive surviving for the longest. Their evaporation belongs to a future far beyond the death of the last star, so we need not follow it in detail tonight. It is enough to notice what the starless darkness really contains: cooling remnants, changing orbits, rare collisions, gravitational waves, scattered radiation, and unanswered physics. The universe after stars is not a blank page. It is a page written in marks too faint and too widely separated for ordinary eyes to read. We have now reached the answer hidden beneath the title. When the last star dies, the cosmos does not end and change does not cease. One luminous era closes while a far darker era continues through gravity, quantum physics, and the slow loss and redistribution of energy. What we know is that stars exhaust their usable fuel and leave remnants. What models suggest is that those remnants continue interacting across extraordinary spans of time. What remains unknown is how matter and the laws governing it behave when those spans become almost limitless. There is no failure in that uncertainty. It is simply the honest edge of the journey. In the final part, we can leave the remnant darkness behind, return to the stars above your room tonight, and give the last star its quiet place in the much larger history of the universe. The death of the last star will not be the death of the universe. It will be the end of a particular way the universe has been shining, the long era in which gravity gathered hydrogen into stars, nuclear fusion warmed their interiors, and steady light spread outward across the darkness. By the time that final star reaches its end, almost every familiar feature of the present sky will already have vanished. The bright clusters will be gone, the glowing nebulae will have faded, spiral galaxies will no longer be traced by young blue stars. Somewhere within one old gravitationally bound region, a small and patient star will complete the same transformation that countless others completed before it. Its hydrogen fusion will weaken its structure, will change, and it will settle into a compact remnant. Nothing will tear the whole cosmos apart at that moment. No signal will announce a universal ending. One final stellar furnace will simply cease to be a star. What we know most confidently comes from the physics of stars we can observe today. Massive stars consume their fuel rapidly and disappear early. Stars like the Sun last much longer, but they too eventually leave ordinary fusion behind. The lowest mass red dwarfs burn more slowly and can use a larger fraction of their hydrogen, allowing them to survive for times far beyond the present age of the universe. We also know that galaxies are gradually becoming less active in producing new stars. As accessible cold gas is consumed, heated, dispersed, or locked into long-lived objects and remnants. These observations and physical principles point toward a future in which faint red dwarfs dominate the remaining starlight. The details lie far ahead, but the direction is clear. Brightness fades first. Patience remains. What the models suggest is more distant and therefore less certain. Ancient red dwarfs may gradually become hotter, before ending as compact white dwarfs. Rare collisions between brown dwarfs may occasionally produce new low-mass stars after ordinary galactic star formation has nearly ceased. The last star to shine may therefore not be the oldest survivor. It could be a late arrival assembled by chance from objects that had wandered through darkness for ages. These possibilities make the final stellar era uneven. Starlight may disappear from one region, return faintly after an extraordinary interval, and then fade again. The literal last star would be determined by a mixture of stellar physics and improbable gravitational encounters. We can describe its likely character, but we cannot know its address. There will be no convenient label attached to the final red point. Beyond that lies what remains unknown. We do not know the exact nature of dark matter or dark energy. We do not know whether protons are perfectly stable across unlimited time. We do not know whether unfamiliar physical processes become important during eras far longer than anything the universe has yet experienced. Even the phrase "the last star in the universe" carries a limitation, because distant regions may become permanently separated by cosmic expansion. No observer in one region could confirm that another star was not still shining beyond an unreachable horizon. The last star is therefore partly a global idea in a cosmological model, not necessarily an event that anyone could witness and verify. Scientific uncertainty here is not an empty space filled with guesses. It is a boundary carefully marked by what observations and tested theories can support. After starlight ends, remnants will continue to cool and move. White dwarfs will release stored heat. Neutron stars and black holes will persist. Planets and brown dwarfs may travel through old systems or drift alone. Gravitational encounters will slowly rearrange orbits, eject objects, and occasionally bring compact bodies together. Rare mergers or accretion events may create brief flashes, while gravitational waves cross regions too dark for ordinary vision. Background photons will continue stretching through expanding space. The cosmos will contain energy structure and change even when eyes like ours would see almost nothing. The final star closes the stelliferous era, but it does not close every future chapter. The library remains though the reading lamps have gone dark. And now, after travelling so far forward, we can return to the quieter and much younger universe around you. Perhaps there is a window nearby with only a few stars visible through city light. Perhaps the sky outside is clouded and the stars are hidden rather than absent. Or perhaps you're beneath a dark sky where the Milky Way can still be seen as a pale band across the night. Every star visible now belongs to an era of extraordinary abundance. Galaxies are still making new suns. Red dwarfs have barely begun their long lives. The universe has not yet produced a naturally exhausted one. The final stellar flame lies trillions of years beyond us, farther into time than any journey can comfortably picture. So the clearest answer is gentle. When the last star dies, ordinary starlight will end, but the universe will continue. Matter will remain unless deeper physics eventually changes it. Gravity will continue shaping motion. Remnants will cool, collide, merge and separate. Radiation will travel through the darkness, becoming fainter and more stretched. The cosmos will be different beyond recognition, but not suddenly erased. One era will have completed its work. Tonight, however, that ending is unimaginably distant. Above your room, stars still fill the galaxy. Their light is crossing space now, arriving quietly at Earth, after journeys lasting years, centuries or longer. For a little while in cosmic history, the universe is bright enough to reveal its past, and we are here to notice. There is no need to hold the whole future in your thoughts. Let the final star remain far away, shining faintly at the edge of imagination. The night around you is still rich with light, and you may rest beneath it.